The San Andreas Fault has been responsible for some of California's most devastating earthquakes, from the 1906 San Francisco disaster to the 1989 Loma Prieta quake. But according to the latest geological evidence, these historical events may have been just warm-ups compared to what this fault system is truly capable of producing. New research from 2025 has drilled deep cores revealing prehistoric ruptures spanning over 600 kilometers, exceeding the 1906 rupture by 25%. These ancient mega-earthquakes reached similar or even larger magnitudes than anything in recorded history, suggesting that California's seismic future could be far more violent than anyone imagined. What makes this discovery particularly unsettling is how it changes our understanding of the risks facing millions of people living directly above this geological giant. California's underground time bomb. Beneath the surface, nearly 40 million people across California are grabbing their morning coffee, sitting in traffic, or heading to work without giving a second thought to what exists just beneath the pavement under their feet. In Los Angeles, office workers hurry past gleaming skyscrapers that stretch toward the sky. In San Francisco, commuters cross the Bay Bridge while fog rolls in from the Pacific. In San Diego, families stroll along beaches where waves crash against the shore. All of this everyday activity happens above one of the most powerful and dangerous geological features on the planet. While millions of Californians go about their normal routines on the surface, massive forces are building pressure in the rock layers far below them. These aren't small, insignificant movements. The Pacific Plate and the North American Plate are locked in a slow-motion collision that has been going on for millions of years, and the stress from this ongoing battle accumulates every single day. Each year that passes without a major earthquake means more energy gets stored in the rock, like winding up a giant spring that will eventually have to release all that built-up tension. Most people think of the San Andreas as a single crack running through California, but that understanding misses the true scope of what scientists are dealing with. The San Andreas isn't just one fault. It's an entire network of interconnected fractures that spans over 800 miles from the Salton Sea in the south to Cape Mendocino in the north. This system includes 3 major sections that geologists have identified through USGS research, each with distinct characteristics that can influence each other in ways that scientists are only beginning to understand. The complexity of this fault network means that stress doesn't just build up in one location. Instead, pressure accumulates across multiple sections simultaneously, and when one part of the system finally gives way, it can trigger movements along other connected faults. This domino effect has happened before in California's geological history, and recent monitoring data suggests it could happen again. The fault system has been accumulating stress for decades without a major release, and some sections haven't experienced significant movement for over a century. To understand why California sits on such dangerous ground, you need to know how tectonic plates actually work. The Earth's surface consists of massive slabs of rock called tectonic plates that float on the semi-liquid mantle below. These plates move constantly, but at speeds measured in centimeters per year rather than feet or miles. When plates interact with each other, they can push together, pull apart, or slide past each other horizontally. The San Andreas represents the third type of interaction, called a transform boundary, where 2 plates slide past each other in opposite directions. The Pacific Plate moves northwest at about 8 centimeters per year, while the North American Plate moves southeast at roughly 2.3 centimeters per year. This might not sound like much movement, but over millions of years, these plates have traveled hundreds of miles relative to each other. The transform boundary mechanics create a situation where the plates don't slide smoothly past each other like 2 pieces of paper. Instead, they get stuck together along their boundary because of friction and the irregular shapes of the rock surfaces. As the plates continue trying to move, stress builds up in the rocks along the fault line. Eventually, this stress overcomes the friction holding the plates together, and they suddenly slip past each other, releasing all the accumulated energy in the form of an earthquake. This process affects over 40 million people who live in California, many of them concentrated in major metropolitan areas that sit directly on or very close to fault lines. Los Angeles County alone has nearly 10 million residents, and much of the region lies within 50 miles of active fault zones. The San Francisco Bay Area, home to over 7 million people, sits on multiple fault systems including the San Andreas, Hayward, and Calaveras faults. These aren't rural areas with scattered populations. These are some of the most densely populated and economically important regions in the United States. The 2025 monitoring data has revealed patterns that concern scientists who study earthquake activity. Advanced sensor networks now track ground movement with precision that was impossible just a few years ago. These sensors detect tiny changes in the Earth's surface, shifts in groundwater levels, and subtle alterations in the stress patterns along fault lines. The data shows that several sections of the San Andreas system are experiencing changes in their behavior, with some areas showing increased micro-earthquake activity, while others remain ominously quiet. What makes this recent data particularly troubling is that it reveals connections between different parts of the fault system that scientists didn't fully understand before. Advanced computer modeling now shows how stress transfer works between fault segments, and how movement in one area can increase pressure in distant sections. This interconnected nature means that predicting when and where the next major earthquake will occur becomes much more complicated than simply monitoring individual fault segments. The fault system's complexity extends far beyond what you can see on the surface. While the main San Andreas fault creates visible scars across the landscape in places like the Carrizo Plain, most of the system exists deep underground where it's impossible to observe directly. The fault zone itself can be several miles wide in some locations, with multiple parallel fractures that can rupture independently or in conjunction with larger events. Recent deep drilling projects and advanced imaging techniques have revealed that the San Andreas fault system reaches much deeper into the Earth's crust than previously thought. Some sections extend more than 20 miles down, passing through different types of rock that respond to stress in various ways. This vertical complexity adds another layer of unpredictability to how the fault system behaves during major earthquakes. The 2025 research has also uncovered evidence that the fault system is far more dangerous than previous generations of scientists understood. New paleoseismic studies, which examine the geological record of past earthquakes, show that the San Andreas has produced massive earthquakes throughout its history that exceed the magnitude of any earthquake experienced by modern California. These prehistoric events moved enormous sections of the landscape and created surface ruptures that extended for hundreds of miles. But the most alarming discovery came when researchers realized that this massive fault system doesn't behave as a single entity at all. The three-headed monster. Scientists studying the San Andreas fault system discovered something that changed how they understand California's earthquake risk. The fault doesn't behave like a single massive crack running through the state. Instead, it acts like three completely separate entities, each with its own personality, its own history, and its own way of building up and releasing stress. These three sections operate independently most of the time, but they can also communicate with each other in ways that make the entire system far more dangerous than anyone previously realized. The northern section stretches from San Francisco Bay up to Cape Mendocino and has earned a reputation as the most violent of the three segments. This section doesn't mess around when it decides to move. On April 18, 1906, the northern segment unleashed its fury in what became known as the Great San Francisco Earthquake. The rupture started near San Francisco and tore through the landscape for over 290 miles, reaching as far north as Point Arena. Buildings collapsed, fires raged for days, and over 3,000 people lost their lives. The earthquake registered an estimated magnitude of 7.9, but recent analysis of the 1906 event using modern techniques suggests the actual energy release may have been even greater than originally calculated. What makes the northern section particularly concerning is how completely it ruptures when it finally gives way. The 1906 earthquake didn't just crack the surface in a few places. It created a continuous zone of destruction that extended for hundreds of miles, with some areas experiencing ground displacement of up to 20 feet. Fence lines were offset, roads were torn apart, and entire hillsides shifted position. The geological evidence shows that when the northern section decides to move, it moves big and it moves fast. Current monitoring data from 2025 indicates that stress has been building along this segment again, though not yet to the levels that preceded the 1906 event. The central section presents a completely different challenge for scientists trying to understand fault behavior. This segment runs from the San Francisco Bay area down to Parkfield and exhibits something called fault creep. Instead of locking up and building stress like its northern and southern neighbors, the central section moves gradually and continuously at a rate of about 1 inch per year. For decades, scientists thought this steady creeping motion meant the central section was relatively safe because it was constantly releasing stress rather than accumulating it. This assumption turned out to be dangerously wrong. Recent paleoseismic research has uncovered evidence that the central section has produced major earthquakes in the past, despite its current creeping behavior. The geological record shows that this section can switch between creeping and locked behavior over time periods measured in centuries. When it transitions from creeping to locked mode, it can accumulate stress just like the other sections and eventually produce significant earthquakes. The 2025 monitoring data shows subtle changes in the creeping rate that some scientists interpret as early signs of a potential transition toward more locked behavior. The southern section represents the most ominous threat of all three segments. This portion of the fault system extends from Parkfield down to the Salton Sea and hasn't experienced a major earthquake since the last significant rupture occurred between 1721 and 1731. That might sound like good news, but it's actually terrifying from a geological perspective. The longer a fault section remains locked without releasing stress, the more energy accumulates in the surrounding rocks. The southern section has been building up stress for nearly 3 centuries, while the Pacific and North American plates continue their relentless movement. Historical records and geological evidence suggest that the southern section typically produces major earthquakes every 200 to 300 years based on paleoseismic data from USGS studies. The last significant rupture means this segment is already approaching its average recurrence interval. Some sections of the southern San Andreas haven't moved substantially in even longer time periods. This prolonged quiet period means that when the southern section finally does rupture, it could produce an earthquake significantly larger than anything California has experienced in recorded history. According to Yusuf 3 probability models, there's a 93% chance of a magnitude 7 or greater earthquake occurring by 2045. The 3 sections don't operate in complete isolation from each other. Modern seismic monitoring reveals that they communicate through a process called stress transfer. When one section ruptures, it changes the stress patterns in the adjacent sections, potentially bringing them closer to their own breaking points. This domino effect has happened before in California's geological past and could happen again. The 1906 northern section earthquake actually increased stress on the central section, though it took decades for that additional stress to become apparent in the geological record. Current 2025 seismic data shows stress levels in all 3 sections that concern earthquake researchers. The northern section has accumulated significant stress since 1906, though it hasn't yet reached the critical threshold that preceded that massive earthquake. The central section shows signs of transitioning away from its steady creeping behavior toward a more locked state. Most troubling of all, the southern section continues to accumulate stress at rates that suggest it's approaching a critical breaking point. New monitoring technology deployed across California reveals previously unknown connections between the 3 fault sections. Networks of sensitive seismic instruments detect micro-earthquakes and tiny ground movements that were invisible to older monitoring systems. This technology shows that small earthquakes in one section can trigger increased activity in distant parts of the fault system. GPS stations track ground movement with millimeter precision, revealing how stress transfers between sections in real time. The data from these advanced monitoring systems paints a concerning picture of current conditions along the San Andreas fault system. All three sections show signs of increased stress accumulation, and the communication between sections appears to be increasing. Small earthquakes in the central section correlate with subtle changes in stress patterns measured in the southern section hundreds of miles away. Similarly, minor seismic activity near the northern section coincides with changes in the creeping rate of the central segment. Perhaps most alarming is the evidence suggesting that all three sections may be approaching critical stress thresholds simultaneously. This hasn't happened in recorded California history, and the geological record suggests it's a rare occurrence even over longer timescales. Computer models based on 2025 data indicate that if multiple sections were to rupture in sequence or simultaneously, the resulting earthquake could exceed magnitude 8.0 and affect the entire state of California. The prolonged quiet of the southern section becomes even more terrifying when viewed in the context of what's happening in the other two segments. While the northern and central sections show various signs of increased activity and stress accumulation, the southern section remains ominously silent. This silence doesn't indicate stability. Instead, it suggests that this section is locked so tightly that it's not even producing the small earthquakes and micro-movements that typically precede major ruptures. The 2025 monitoring data confirms that the southern section is storing enormous amounts of energy that will eventually demand release in a catastrophic earthquake event. But understanding the true scope of what the San Andreas system can produce requires looking far beyond the earthquakes recorded in human history, deep into the geological record where evidence of the fault's most devastating ancient behavior lies buried. When the Earth rewrites history. Scientists working in 2025 have been digging trenches across California's landscape, but they're not looking for buried treasure or ancient artifacts. These researchers are hunting for something far more valuable and terrifying: evidence of earthquakes that happened thousands of years before humans started keeping written records. Their discoveries have revealed that the San Andreas fault system has produced catastrophic events throughout its history that make modern California earthquakes look like minor tremors by comparison. The detective work these paleoseismic researchers perform requires incredible patience and precision. They dig carefully planned trenches that cut directly across fault lines, exposing cross-sections of rock and sediment layers that have accumulated over thousands of years. Each layer tells a story about what was happening on the Earth's surface when it was deposited. Scientists look for specific clues that indicate when major earthquakes occurred: offset rock layers where the fault suddenly shifted, broken and displaced sediment deposits, and organic materials like charcoal and plant remains that can be radiocarbon dated to establish precise timelines of past ruptures. The methodology involves examining every detail visible in these trench walls. When a major earthquake occurs, it leaves unmistakable signatures in the geological record. Rock layers that were once continuous get broken and offset by the fault movement. Sediment deposits show evidence of sudden disruption and displacement. Sometimes entire sections of the trench wall show evidence of multiple earthquake events stacked on top of each other, creating a timeline of seismic activity that extends back thousands of years. What these 2025 investigations have uncovered defies what most people understand about California's earthquake history. The geological record reveals evidence of prehistoric mega-earthquakes that released energy far exceeding anything California has experienced in recorded history. These ancient events didn't just shake buildings and crack roads. They fundamentally altered the landscape across hundreds of miles, offsetting ridges by tens of meters and redirecting ancient river channels. The scale of these prehistoric earthquakes becomes clear when scientists examine the geological evidence of surface ruptures. The 1857 Fort Tejon earthquake, which ranks among California's largest historical events, created a surface rupture that extended about 350 kilometers along the fault line. The maximum ground displacement in some areas reached 9 meters, enough to completely offset roads, fence lines, and any other human-made features that happened to cross the fault. Some paleoseismic ruptures approached similar distances of 350 kilometers, longer than most historic events, but representing the true potential of this fault system. These ancient mega-earthquakes left permanent marks on California's topography. Geological evidence shows that some prehistoric events shifted entire hillsides and ridge lines by distances measured in tens of meters, rather than the single-digit meter displacements typical of modern California earthquakes. River systems that had been flowing in the same channels for thousands of years were suddenly redirected when fault movement created new topography. Valley floors were uplifted into hills, and hills were dropped into new valleys. The landscape that exists today in many parts of California reflects the cumulative effects of these massive prehistoric seismic events. The timing patterns of these mega-earthquakes reveal something particularly concerning about how the San Andreas fault system operates over long time periods. Rather than producing large earthquakes at regular intervals, the geological record shows evidence that the largest earthquakes tend to occur in clusters. Trenching data reveals 4 paleoseismic events that exceeded current recurrence intervals, suggesting periods of intense seismic activity followed by longer quiet phases. The southern section of the San Andreas Fault shows particularly strong evidence of this clustering behavior. Paleoseismic studies indicate that this section has experienced 7 major earthquakes over the past 1,000 years, with timing patterns that suggest these events don't occur randomly, but follow recognizable sequences related to how stress accumulates throughout the fault system. Surface rupture evidence from these prehistoric events extends for distances that challenge modern understanding of fault behavior. While the 1906 San Francisco earthquake created a continuous rupture zone extending about 470 kilometers, geological evidence of some prehistoric events shows rupture zones approaching the maximum observed lengths of individual fault segments. These massive ruptures involved movement along multiple connected fault sections that demonstrate the true scope of what the San Andreas system can produce. The energy release from these prehistoric mega-earthquakes carved permanent scars into California's landscape. Ancient lake beds show evidence of sudden uplift that drained entire water bodies. Mountain passes were created when fault movement dropped sections of ridge lines below the surrounding peaks. Coastal areas show evidence of sudden elevation changes that moved shorelines by significant distances in single earthquake events. These landscape modifications happened in minutes or hours, rather than the gradual geological processes that typically reshape terrain over millions of years. Current conditions along the San Andreas fault system show disturbing similarities to the geological signatures that preceded previous major earthquake episodes. The southern section hasn't experienced a major rupture in over 300 years, which places it well into the time range when previous clustering episodes began. Stress measurements from 2025 monitoring networks indicate that multiple sections of the fault system are approaching critical thresholds simultaneously, a condition that hasn't existed since the last major clustering episode several centuries ago. The possibility that California may be entering another period of major earthquakes represents a seismic threat unlike anything the state has faced in its modern history. The prehistoric events revealed by 2025 paleoseismic research suggest that when the next major earthquake cycle begins, it could involve multiple large events occurring within decades of each other. These events would affect the entire state rather than just regional areas, and their cumulative impact would exceed anything that current emergency planning and building codes are designed to handle. The geological evidence points toward a disturbing conclusion about California's seismic future, but the full picture of what makes the next major earthquake potentially more devastating than anything in the prehistoric record requires understanding an unexpected factor that most people would never connect to earthquake activity. This unexpected factor lies hidden beneath the desert waters of Southern California's most overlooked lake. Most people driving through the Imperial Valley probably don't think much about the Salton Sea, that odd inland lake sitting in the middle of the desert about 150 miles east of San Diego. The lake looks pretty unremarkable from the highway, just another body of water in a landscape that doesn't seem like it should have any water at all. But this strange lake holds the key to understanding why the next major earthquake on the southern San Andreas fault could be more devastating than any seismic event in California's recorded history. The Salton Sea that exists today represents just a tiny fraction of what once covered this desert valley. For thousands of years, an enormous lake called Lake Cahuilla filled the entire Coachella Valley and extended deep into Mexico. This ancient lake was absolutely massive compared to what visitors see today. Where the current Salton Sea covers about 350 square miles with a maximum depth of around 50 feet, Lake Cahuilla stretched across more than 2,000 square miles and reached depths of 300 feet in some areas. The ancient lake held approximately 40 times more water than today's remnant, creating a body of water that would have rivaled some of the Great Lakes in size and depth. Lake Cahuilla didn't maintain constant water levels throughout its existence. Instead, it went through cycles of filling and drying that lasted several centuries each. During wet periods, the Colorado River would change course and flow into the valley, gradually filling the basin over decades or centuries. During dry periods, the inflow would stop and the lake would slowly evaporate under the desert sun, leaving behind salt flats and dried lake beds. These cycles repeated over thousands of years, creating a pattern that scientists can read in the geological record through sediment layers and shoreline deposits left behind at different elevations. The connection between Lake Cahuilla's water levels and earthquake activity along the southern San Andreas fault took scientists decades to recognize, but once they understood the relationship, it changed everything about how they view seismic risk in Southern California. Research shows a remarkable correlation between the presence of this massive lake and the timing of major earthquakes on the fault system. Over the past 1,000 years, the southern San Andreas fault has experienced 7 significant earthquakes. 6 of those 7 events occurred during periods when Lake Cahuilla was either completely full or in the process of filling with water, according to SDSU paleoseismic studies. The mechanism behind this correlation involves how water weight and pressure affect the deep underground mechanics of fault systems. When Lake Cahuilla was full, it held trillions of gallons of water that pressed down on the Earth's surface with enormous weight. This water pressure didn't just affect the surface rocks. It penetrated deep into cracks and fractures in the Earth's crust, reaching down toward the fault zone itself. The weight of all that water created additional stress on the fault system, but it also provided a critical mechanical effect that made it easier for the fault plates to slip past each other when stress levels reached critical thresholds. The water from Lake Cahuilla could seep into underground fractures and fault zone materials, changing the physical properties of the rocks along the fault line. Water infiltration unclamps faults, reducing friction and advancing rupture timing. When the fault zone experiences this unclamping effect, it takes less accumulated stress to trigger a major earthquake. The massive lake essentially made it easier for the southern San Andreas fault to release built-up tension before stress levels reached truly dangerous levels. The Salton Sea has been shrinking steadily for over a century, and this decline represents a fundamental change in the conditions that have influenced earthquake timing for thousands of years. The current lake receives water primarily from agricultural runoff and has no natural inflow source like the ancient Lake Cahuilla did. As water usage patterns change and agricultural practices become more efficient, less water reaches the Salton Sea each year. The lake level drops steadily, and the total volume of water continues to decrease. This ongoing shrinkage means that the water pressure and unclamping effects that once influenced the southern San Andreas fault system are disappearing. Without the massive weight and pressure from Lake Cahuilla, the southern San Andreas fault now operates under completely different mechanical conditions than it has for most of its history. The absence of water pressure allows unprecedented stress accumulation along the fault zone. The plates continue their relentless movement, grinding against each other and building up tension, but without the water infiltration that once made it easier for them to slip, the fault segments remain locked together much more tightly. This increased locking means that when the fault finally does rupture, it will release far more accumulated energy than would have been possible when Lake Cahuilla was present. Current stress measurements from 2025 monitoring networks confirm that the southern section of the San Andreas fault is experiencing stress accumulation rates that exceed anything measured in previous decades. Advanced instrumentation shows that the fault zone is locked more tightly than scientists have ever recorded, with some sections showing virtually no movement at all despite the continuous pressure from tectonic plate motion. GPS stations throughout the region detect the gradual buildup of strain as the Pacific and North American plates continue trying to move past each other while the fault remains frozen in place. The implications of this stress accumulation become clear when scientists model potential earthquake scenarios based on current conditions. Without the moderating influence of Lake Cahuia's water pressure, the next major earthquake on the southern San Andreas fault will likely involve much larger ground displacements and energy release than previous events. The last significant rupture on this section occurred sometime between 1721 and 1731, producing a magnitude 7.3 or 7.4 earthquake with ground displacements of 12 to 14 feet. Given that over 300 years have passed since that event, and considering the absence of the ancient lake's moderating effects, scientists now estimate that the next earthquake could involve displacements of up to 16 feet. These increased displacement predictions translate directly into higher magnitude estimates for the next southern San Andreas earthquake. Computer models based on 2025 research suggest that the missing lake effect could increase the earthquake magnitude by a full point compared to what would have occurred under historical conditions. Instead of expecting a magnitude 7.3 or 7.4 earthquake like the last major event, scientists now predict that the next rupture could reach magnitude 7.5 or higher. A magnitude increase of 1 full point represents a 10-fold increase in energy release, meaning the next earthquake could be 10 times more powerful than it would have been if Lake Cahuia still existed. The absence of Lake Cahuia has essentially removed a natural safety valve that once helped regulate earthquake timing and intensity along the southern San Andreas fault. Without this moderating influence, the fault system is building toward a catastrophic release of energy that will exceed anything California has experienced in its recorded history. The scale of destruction this earthquake could cause depends entirely on what now sits directly above this geological time bomb. Cities built on borrowed time. When the last major earthquake struck the southern San Andreas fault in 1857, Los Angeles was nothing more than a dusty frontier town with fewer than 5,000 residents scattered across adobe buildings and dirt roads. The Fort Tejon earthquake shook the ground violently, but it affected relatively few people because so few people lived anywhere near the fault line. Fast forward to 2025, and that same stretch of the San Andreas fault now threatens over 9 million people living in Los Angeles County alone, with the greater Southern California region housing over 20 million residents who go about their daily lives completely unaware that they're living on borrowed time. The transformation of Los Angeles from a small frontier settlement to one of America's largest metropolitan areas represents one of the most dramatic population explosions in human history. In 1857, you could walk from one end of the town to the other in about 20 minutes. Today, the Los Angeles metropolitan area stretches across 5 counties and covers over 33,000 square miles. Freeways carry millions of commuters every day through areas that were completely uninhabited when the last major earthquake occurred. Shopping centers, office buildings, schools, and hospitals now occupy land that was nothing but empty desert and farmland during the 19th century. San Francisco presents an equally sobering example of how population growth has amplified earthquake risk since the last major seismic event. When the 1906 earthquake struck, San Francisco had a population of around 400,000 people living in mostly wooden buildings that caught fire easily after the shaking stopped. The earthquake and subsequent fires destroyed about 80% of the city and killed approximately 3,000 people. Today, the San Francisco Bay Area houses over 7.7 million residents in a complex urban environment that includes high-rise buildings, extensive transportation networks, and critical infrastructure systems that didn't exist in 1906. The modern infrastructure that defines California's major cities creates entirely new categories of earthquake hazards that previous generations never had to consider. High-rise buildings constructed with steel and concrete can withstand earthquake shaking much better than the wooden structures of 1906, but they also create different types of risks. When tall buildings sway during earthquakes, they can collide with adjacent structures or suffer internal damage that isn't immediately visible. Glass facades can shatter and fall onto crowded sidewalks below. Elevators can become death traps when they lose power or their cables snap during violent shaking. Underground infrastructure presents even more complex challenges during major earthquakes. Modern cities depend on vast networks of water mains, gas lines, electrical conduits, and communication cables that run beneath streets and buildings. When these underground systems rupture during earthquakes, they can create cascading failures that affect entire regions. Broken gas lines can cause fires that spread rapidly through dense urban areas. Severed water mains eliminate the water pressure needed to fight those fires. Damaged electrical systems can leave millions of people without power for weeks or months after a major earthquake. The concentration of critical facilities directly on or very close to fault lines represents one of the most concerning aspects of California's current vulnerability. Hospitals that would be desperately needed after a major earthquake sit within a few miles of active fault segments. Schools housing thousands of children operate in buildings that could collapse or suffer severe damage during strong shaking. Emergency response centers and fire stations that communities depend on for disaster response are located in areas that could become inaccessible when roads crack and bridges fail. Los Angeles International Airport, one of the busiest airports in the world, sits about 35 miles from the southern San Andreas fault and handles over 80 million passengers every year. The airport's runways, terminals, and air traffic control systems could all suffer significant damage during a major earthquake, potentially stranding hundreds of thousands of travelers and disrupting air transportation across the entire western United States. Similarly, the ports of Los Angeles and Long Beach, which handle about 40% of all containerized goods entering the United States, could be shut down for months if earthquake damage affects their loading facilities, cranes, and transportation connections. The 2025 population data reveals the staggering scale of potential impact that a major southern San Andreas earthquake could produce. Nearly 40 million people now live within 30 miles of an active fault in California, an area that was largely unpopulated during previous major earthquakes. This population density means that even a moderate earthquake could affect more people than the largest historical California earthquakes simply because of how many more people now live in the affected areas. A magnitude 7.5 earthquake on the southern San Andreas could directly impact more residents than live in most entire states. Urban sprawl has pushed residential development into previously unpopulated areas that happen to sit in particularly dangerous locations relative to fault lines. Housing developments now cover hillsides that are prone to landslides during earthquake shaking. Subdivisions spread across valley floors where soft sediments can amplify seismic waves and cause more severe shaking than would occur on solid rock. Retirement communities and mobile home parks occupy areas that were considered too risky for development just a few decades ago, but now house thousands of vulnerable residents. The economic implications of this massive population growth become clear when you consider current property values and infrastructure investments throughout earthquake-prone regions of California. Real estate in Los Angeles County alone represents over $2 trillion in property value, much of it located within areas that could experience severe shaking during the next major earthquake. Commercial buildings, industrial facilities, and residential properties worth hundreds of billions of dollars sit directly in the path of potential earthquake damage. The concentration of people and infrastructure along earthquake-prone areas of California has created a situation where the next major earthquake will affect exponentially more people than any previous seismic event in the state's history. While the 1906 San Francisco earthquake impacted several hundred thousand people, the next major southern San Andreas earthquake could directly impact tens of millions of people and indirectly affect the entire state's economy and infrastructure systems. This massive increase in population and infrastructure development has occurred during a period when the southern San Andreas fault has remained relatively quiet, creating a false sense of security among residents and policymakers who haven't experienced a major earthquake in their lifetimes. The geological processes that drive earthquake activity continue operating regardless of human development patterns, meaning that the fault system will eventually release its accumulated stress, whether 20 million people live nearby or just a few thousand. Fortunately, scientists now have access to monitoring technology that provides unprecedented insight into exactly what's happening deep beneath California's surface. The technology revolution. Advanced monitoring systems deployed throughout California reveal ground movements and seismic patterns with precision that would have been impossible just a few years ago. Compared to 2019's ShakeAlert baseline, 2025 systems integrate GNSS and fiber sensing technologies that have transformed earthquake detection from reactive monitoring to proactive threat assessment. The USGS now operates approximately 1,600 seismometers plus 500 GNSS stations across the state, creating a comprehensive network that captures seismic activity with unprecedented detail and accuracy. These monitoring stations represent just one component of a much larger technological ecosystem that includes accelerometers measuring ground acceleration in 3 dimensions, GPS stations tracking millimeter-scale movements in real time, strain meters detecting tiny changes in rock stress, and tilt meters sensing when the ground surface tilts by microscopic amounts. Each sensor feeds data continuously to central processing centers where supercomputers analyze millions of data points every second, searching for patterns that indicate earthquake activity or stress accumulation along fault lines. Artificial intelligence and machine learning algorithms now handle the massive task of analyzing earthquake patterns in real time across this enormous sensor network. These systems process data from thousands of monitoring stations simultaneously, comparing current readings against historical patterns and identifying anomalies that human analysts might miss or take hours to recognize. The AI systems learn from every earthquake they detect, constantly refining their ability to distinguish between actual seismic events and false signals caused by construction equipment, traffic, or weather phenomena. Machine learning algorithms can now identify subtle precursor signals that sometimes occur before major earthquakes, patterns so complex that traditional analysis methods couldn't detect them. The ShakeAlert system received major upgrades throughout 2024 and 2025 that transformed it from a promising experimental program into a comprehensive early warning network covering the entire West Coast. The system now processes information from over 1,600 seismic monitoring stations and can issue earthquake alerts within seconds of detecting strong ground motion. Recent improvements include better magnitude estimation algorithms that use real-time satellite data from global navigation satellite systems to provide more accurate assessments of earthquake size and potential impact. The enhanced system can now provide warnings for earthquakes as small as magnitude 4.5 in some areas, giving people crucial seconds to take protective action before dangerous shaking arrives. Satellite technology has reached the point where it can detect ground movements measured in millimeters from hundreds of miles above the Earth's surface. Advanced radar satellites continuously monitor California's landscape, measuring tiny changes in elevation and horizontal position that indicate stress accumulation along fault lines. This space-based monitoring provides a comprehensive view of how the entire state is deforming as tectonic plates continue their relentless movement. The satellite data reveals patterns of ground movement that were completely invisible to previous generations of monitoring technology, showing how stress transfers between fault systems and accumulates in specific areas over time. One of the most significant technological developments involves turning California's existing fiber optic cable networks into earthquake sensors. The same cables that carry internet traffic and phone calls can detect seismic waves through a process called distributed acoustic sensing. The adapted physics-based algorithm processes data from any fiber network, mitigating urban noise, according to Hudson et al. 2025 research. This technology essentially transforms thousands of miles of existing infrastructure into a dense network of earthquake sensors without requiring any new construction or installation. Fiber optic sensing provides particularly detailed information about how seismic waves travel through urban areas where traditional monitoring stations would be difficult to install. GPS networks throughout California now track tectonic plate movement with precision that approaches the theoretical limits of measurement accuracy. These GPS stations can detect horizontal movements of less than 1 millimeter per year and vertical movements of just a few millimeters annually. The network reveals exactly how fast different parts of California are moving relative to each other as the Pacific and North American plates grind past each other. This precise tracking allows scientists to measure stress accumulation rates along fault segments and identify areas where movement is temporarily blocked, indicating potential earthquake hazard zones. Smartphone applications have become an integral part of California's earthquake detection network through programs like the MyShake app developed by UC Berkeley. The accelerometers built into modern smartphones can detect earthquake shaking and automatically transmit that information to central monitoring centers. With over 3.7 million downloads, the MyShake app creates a distributed network of sensors carried by ordinary citizens throughout the state. The app has already provided early warning for recent earthquakes, giving users up to 15 seconds of advance notice before strong shaking reached their locations. Recent updates include audio messages in 6 different languages and improved background processing that provides more accurate magnitude information. The 2025 early warning capabilities represent a quantum leap in public safety technology compared to what was available during previous major California earthquakes. The integrated system can now detect earthquake initiation within seconds, estimate magnitude and affected areas almost instantly, and deliver targeted warnings to specific geographic regions based on predicted shaking intensity. Emergency response agencies receive detailed impact assessments within minutes of major earthquakes, allowing them to deploy resources more effectively. Schools, hospitals, and critical infrastructure facilities can receive automated alerts that trigger protective protocols like stopping elevators, shutting off gas lines, and securing hazardous materials. This comprehensive technology network detected concerning new patterns in seismic activity during 2024 and 2025 that weren't visible to previous monitoring systems. The enhanced sensitivity of current sensors reveals subtle changes in earthquake frequency, stress transfer patterns between fault segments, and previously unknown connections between distant parts of the fault system. AI analysis of this data has identified correlations between small earthquakes in different regions that suggest the entire San Andreas system may be communicating in ways that scientists are only beginning to understand. The integration of all these technological advances creates monitoring capabilities that exceed what most earthquake scientists thought would be possible even a decade ago. California now operates the most sophisticated earthquake monitoring network in human history, with the ability to track ground movements, detect earthquake initiation, estimate impacts, and deliver warnings faster and more accurately than any previous system. However, this technology revolution has revealed something entirely unexpected about what influences earthquake timing and intensity, factors that have nothing to do with traditional geological processes. Advanced monitoring networks have revealed patterns that extend far beyond traditional geological processes. Scientists studying earthquake activity across California have discovered that climate change isn't just affecting weather patterns and sea levels. Research conducted throughout 2024 and 2025 reveals that shifting climate conditions may actually be influencing when and how earthquakes occur along the San Andreas fault system. The connection operates through complex mechanisms that link surface weather patterns to deep underground fault mechanics in ways that researchers are only beginning to understand. California's changing precipitation patterns create direct effects on underground water pressure that can influence fault behavior. When heavy rains soak into the ground during wet years, that water doesn't just sit on the surface. It penetrates deep into rock fractures and soil layers, eventually reaching depths where it can affect the stress conditions around major fault zones. The additional water weight creates extra downward pressure on the Earth's crust, but it also changes fault surface conditions by seeping into cracks and fractures within the fault zone itself. This infiltration effect can make it easier for fault segments to slip when stress levels reach critical thresholds. The opposite effect occurs during extended drought periods when surface water becomes scarce and underground water tables drop significantly. Without adequate water infiltration, fault zones become drier and more tightly locked together. The reduced lubrication means that fault segments can accumulate higher stress levels before finally rupturing, potentially leading to larger earthquakes when they eventually do occur. NASA scientist Paul Lundgren notes that surface water, such as rain and snow, is the largest climate variable that could change fault stress loads, and multiple studies have documented correlations between precipitation patterns and seismic activity levels. Jean-Philippe Avouac's study shows Himalayan micro-earthquakes drop during monsoon season, rising during dry periods. The annual monsoon patterns demonstrate how seasonal weather cycles can influence earthquake timing. Heavy summer precipitation increases stress loads on the Earth's crust and actually decreases microseismicity during wet months. Conversely, the dry winter season sees microseismicity peak as reduced water pressure allows fault segments to move more freely. While these effects primarily influence very small earthquakes, they demonstrate clear connections between surface weather patterns and deep underground fault behavior. Groundwater pumping throughout California's Central Valley and other agricultural regions creates additional complications for fault stress patterns. As farmers and municipalities extract billions of gallons of groundwater each year to compensate for reduced surface water availability, they're essentially removing weight from the Earth's crust. This groundwater extraction doesn't just lower water tables. It actually causes the land surface to sink in a process called subsidence, which changes stress patterns across wide areas, including major fault systems. Research published in Nature demonstrates that groundwater extraction in California's Central Valley can promote lateral stress changes on the San Andreas fault, potentially causing fault segments to unclamp and slip more frequently. These effects don't necessarily trigger major earthquakes, but they can increase the frequency of smaller seismic events while potentially altering the timing of larger ruptures. The study found that intensive groundwater pumping may be causing more frequent but smaller earthquakes along certain fault segments. Sea level rise presents another climate-related factor that affects coastal portions of the San Andreas fault system differently than inland segments. As ocean levels increase due to global warming, the additional water weight along California's coastline creates new stress patterns on fault segments that extend offshore or run close to the ocean. The changing weight distribution doesn't affect all parts of the fault system equally. Coastal segments experience increased pressure from rising seas, while inland segments remain relatively unaffected by this particular climate factor. California's Sierra Nevada mountain range provides direct evidence of how alternating wet and dry periods can affect regional geology in ways that influence fault systems. Research by JPL scientist Donald Argus found that drought and heavy precipitation cycles cause the entire mountain range to rise and fall by approximately 1 inch as water weight changes across the region. These vertical movements create stress changes that can impact faults within or adjacent to the mountain range, potentially influencing earthquake timing along connected fault systems. The 2025 research has uncovered intriguing correlations between California's record-breaking weather patterns and observed changes in seismic activity. The state has experienced unprecedented weather extremes over the past several years, including severe droughts followed by intense atmospheric river events that dump enormous amounts of water across the landscape in short time periods. These rapid transitions between extremely dry and extremely wet conditions create corresponding changes in underground water pressure that may influence fault behavior in ways that scientists are still working to understand. Recent climate extremes have created conditions that didn't exist during previous centuries when the San Andreas fault system established its historical patterns of earthquake timing. The combination of record-breaking droughts, unprecedented groundwater extraction, and rapidly changing precipitation patterns represents a completely new set of environmental conditions affecting fault mechanics. These changes may be disrupting the natural cycles that have governed earthquake timing for thousands of years. Studies from other seismically active regions provide evidence that climate factors can significantly influence earthquake patterns over longer timescales. Research examining earthquakes on the Korean Peninsula over the past 650,000 years shows clear correlations between seismic activity and the end of various ice ages. Each deglaciation event, characterized by rapidly melting ice and rising sea levels, coincided with increased earthquake activity in the region. These findings suggest that major climate transitions can trigger changes in seismic patterns that persist for thousands of years. The 2025 monitoring data suggests that climate factors may be accelerating natural earthquake cycles along the San Andreas fault system. Advanced sensors detect correlations between extreme weather events and subtle changes in fault behavior that weren't visible to previous generations of monitoring technology. The data indicates that rapid climate transitions may be disrupting the gradual stress accumulation patterns that have characterized the fault system throughout its geological history. The emerging evidence points toward a concerning possibility that human-induced climate change may be fundamentally altering the timing and intensity of earthquake cycles throughout California. The combination of changing precipitation patterns, intensive groundwater extraction, and rising sea levels creates an entirely new set of environmental conditions affecting one of the world's most dangerous fault systems. Scientists now have enough data to model exactly what these converging factors mean for California's seismic future. The Big One scenarios. Computer models running on the most advanced supercomputers available in 2025 can now simulate exactly what the next major California earthquake will look like down to individual city blocks. These simulations don't just estimate general shaking levels across broad regions like previous modeling systems did. Instead, they calculate precise ground acceleration values for every neighborhood, every building, and every piece of critical infrastructure throughout the affected areas. The models incorporate detailed geological data about soil types, bedrock depths, and local topography to predict how seismic waves will behave as they travel through different types of ground. Scientists can now tell you that one side of a street might experience violent shaking, while buildings just a few hundred feet away could suffer much less damage, simply because they sit on different types of soil. The block-by-block precision of these 2025 simulations reveals patterns of destruction that nobody anticipated from earlier, less sophisticated modeling efforts. Areas that were previously considered relatively safe now show up as zones of severe shaking due to geological features that amplify seismic waves. Soft sediment deposits in valley floors can increase shaking intensity by 200 to 300% compared to areas built on solid bedrock. Basin effects in places like the Los Angeles metropolitan area create resonance patterns that concentrate earthquake energy in specific neighborhoods while leaving adjacent areas relatively untouched. The new models show exactly which hospitals, schools, fire stations, and emergency facilities will remain functional after major earthquakes, and which ones will be unusable when they're needed most. Modern society's interconnected systems create cascading failure scenarios that dwarf the direct damage from earthquake shaking itself. When the Northridge earthquake struck in 1994, it damaged individual buildings and infrastructure components, but most systems remained largely independent of each other. Today's California operates through networks where every system depends on multiple other systems to function properly. Electric power grids rely on natural gas supplies to fuel generating plants. Communication networks need electricity too. Power cell towers and data centers. Water treatment facilities require both electricity and functioning road networks to deliver chemicals and maintain operations. When major earthquakes damage any component of these interconnected systems, the failures ripple outward through the entire network. The vulnerability created by these modern dependencies exceeds anything previous generations faced during major earthquakes. People living in California during the 1906 San Francisco earthquake or the 1857 Fort Tejon earthquake relied primarily on local resources and simple technologies that could be repaired quickly with basic tools and materials. Today's residents depend on just-in-time delivery systems that transport food, fuel, and essential supplies from hundreds or thousands of miles away. Most grocery stores maintain only 3 to 5 days' worth of inventory, assuming that regular truck deliveries will replenish their shelves. Gas stations receive fuel deliveries every few days from refineries that may be located in other states. When earthquake damage disrupts transportation networks, these supply chains break down within days, creating shortages of basic necessities even in areas that didn't experience severe shaking. Economic impact assessments for the next major California earthquake now predict losses that could exceed the $213 billion estimated by USGS modeling of a magnitude 7.8 earthquake on the southern San Andreas fault. That analysis didn't account for all the indirect costs and supply chain disruptions that would affect the entire national economy. California produces about 15% of the total economic output of the United States, and extended disruptions to the state's economy would have nationwide consequences. The Port of Los Angeles and Port of Long Beach handle about 40% of containerized imports entering the United States, and earthquake damage that shuts down these facilities for months could affect retail prices and product availability across the entire country. Specific earthquake scenarios developed for different fault segments reveal the range of potential impacts depending on exactly where major ruptures occur. A magnitude 7.5 earthquake on the northern section of the San Andreas fault centered near San Francisco would cause severe damage throughout the Bay Area, but would have limited direct impact on Southern California's population centers. The same magnitude earthquake occurring on the southern section near Los Angeles would affect a much larger population and could cause significantly higher casualty numbers due to the greater population density in that region. Southern section ruptures alone would likely remain under magnitude 8.0, according to USGS assessments, though they would still represent catastrophic events for the affected regions. The Uniform California Earthquake Rupture Forecast estimates a 93% probability of a magnitude 7 or greater earthquake hitting California by 2045, with the southern section of the San Andreas Fault being the most at risk. Computer simulations of magnitude 7.8 earthquakes on this southern section predict ground shaking that would collapse thousands of older buildings and severely damage newer structures throughout the Los Angeles metropolitan area. The initial earthquake shaking represents only the beginning of the disaster sequence. Ruptured gas lines would ignite fires throughout the affected region, while damaged water systems would leave firefighters without adequate water pressure to combat the blazes effectively. Emergency response systems will be overwhelmed despite decades of preparation and planning for major earthquake scenarios. California has invested billions of dollars in earthquake preparedness, training programs, and emergency response capabilities, but the scale of a major San Andreas earthquake exceeds the capacity of any emergency response system. The shakeout scenario planning exercises demonstrate that even with perfect coordination and immediate response, emergency services would be unable to reach all affected areas quickly enough to prevent many casualties. Damaged roads and collapsed overpasses would block access to areas where rescue operations are most urgently needed. Hospitals that remain structurally sound after the earthquake would be overwhelmed by casualties, while simultaneously dealing with their own damaged facilities and disrupted supply lines. Long-term recovery challenges facing modern, interconnected society create problems that didn't exist during previous major California earthquakes. Rebuilding efforts after the 1906 San Francisco earthquake took several years, but the city's infrastructure was relatively simple compared to today's complex urban systems. Modern cities depend on sophisticated water treatment plants, electrical distribution networks, communication systems, and transportation infrastructure that require specialized equipment and expertise to repair or replace. Manufacturing. The components needed to rebuild damaged infrastructure often happens in other countries, creating supply chain delays that could extend recovery times for months or years after a major earthquake. The 2025 vulnerability assessments paint realistic pictures of post-earthquake conditions that challenge many assumptions about disaster recovery. Multiple scenario models all point to impacts far exceeding previous California earthquakes in terms of both immediate casualties and long-term economic disruption. The combination of increased population density, complex infrastructure dependencies, and just-in-time supply systems creates vulnerability patterns that didn't exist during any previous major earthquake in California's history. With all this evidence pointing toward unprecedented challenges ahead, the question becomes whether California has enough time to prepare for what's coming. Racing against time. Current scientific evidence points to a timeline that operates on years or decades rather than centuries. Multiple independent indicators now suggest that the probability of a major earthquake occurring within the next few decades has increased substantially compared to previous assessments. Stress measurements along the southern San Andreas fault show accumulation rates that exceed historical patterns. Paleoseismic research reveals that the fault system is overdue for a major release based on its typical recurrence intervals. Advanced monitoring networks detect subtle changes in fault behavior that weren't visible to earlier detection systems. Climate factors may be accelerating natural earthquake cycles in ways that compress traditional timing estimates. California has launched comprehensive preparation initiatives that reflect the urgency suggested by current scientific evidence. The California Governor's Office of Emergency Services is actively promoting earthquake preparedness through statewide programs that recognize earthquakes as a constant threat. These efforts include new educational exhibits, downloadable readiness guides, and social media campaigns designed to reach diverse communities across the state. Public service announcements provide accurate information to newsrooms throughout California. The state government is deploying resources to help residents take actionable preparation steps, rather than simply hoping that major earthquakes won't occur during their lifetimes. Building codes throughout California continue evolving as new understanding of fault behavior emerges from ongoing research. The Alquist-Priolo Earthquake Fault Zoning Act and the Seismic Hazards Mapping Act direct state geologists to identify regulatory zones where higher building standards may be necessary for safe development. These zones include areas prone to surface fault rupture, soil liquefaction, and earthquake-induced landslides. Studies of fault systems provide estimates of maximum earthquake magnitudes and long-term slip rates that serve as basic input for seismic hazard calculations. The information gets distributed to cities, counties, and state construction agencies to guide development decisions in high-risk areas. The California Seismic Hazards Program reviews environmental documents and provides technical comments on geologic hazards that affect land use modification projects. State geologists conduct site reviews of consulting reports for public school and hospital construction projects, ensuring that critical facilities meet enhanced safety standards. Earthquake loss estimation and planning scenarios quantify seismic risk by combining seismic hazard information with data about the vulnerability of existing buildings and infrastructure. These assessments consider consensus values for earthquake rates based on historical activity, fault slip rates, and local soil conditions that can amplify ground shaking. Personal and community preparedness measures have become increasingly urgent as scientific evidence points toward higher earthquake probabilities in the coming decades. The California Earthquake Authority and the California Residential Mitigation Program offer financial assistance and technical guidance for property owners who want to reduce their earthquake risk. These programs provide specialized earthquake insurance coverage that traditional homeowners' policies don't include, creating financial safety nets for property damage. Retrofitting initiatives like Earthquake Brace Plus Bolt offer grants to homeowners for seismic safety enhancements, including foundation bolting and wall bracing that can prevent building collapse during strong shaking. Massive infrastructure retrofitting projects are underway across California to address vulnerabilities in critical systems that millions of people depend on every day. Hospitals, schools, emergency response facilities, and government buildings receive priority for seismic upgrades because they must remain functional after major earthquakes. Transportation infrastructure, including bridges, overpasses, and airport facilities, undergo comprehensive strengthening to prevent catastrophic failures that could isolate communities and hamper emergency response efforts. Water treatment plants, electrical substations, and communication facilities receive seismic upgrades to maintain essential services during post-earthquake recovery periods. Emergency response protocols adapt continuously to incorporate technological capabilities that didn't exist during previous major California earthquakes. The ShakeAlert early warning system now uses over 1,500 seismometers to detect earthquake initiation and issue alerts before strong shaking reaches populated areas. The system incorporates real-time satellite data from global navigation satellite systems to improve magnitude measurement accuracy, which helps emergency responders understand the scale of events they're dealing with. Even a few seconds of advance warning can save lives by allowing people to take protective actions like ducking under tables or pulling vehicles safely off roadways. Individual preparedness plays a crucial role in reducing overall catastrophe impact because emergency response systems will be overwhelmed regardless of how well they're organized and equipped. California's approximately 39 million residents cannot all depend on professional emergency responders for immediate assistance after a major earthquake. People who maintain emergency supplies, secure heavy furniture, and know how to shut off utilities reduce their own risk, while also reducing demands on emergency services that will be desperately needed elsewhere. Community preparedness programs help neighbors organize mutual assistance networks that can provide immediate help when professional responders are occupied with life-threatening emergencies. Current preparation efforts incorporate lessons learned from recent global earthquakes that revealed vulnerabilities in modern interconnected systems. The 2011 earthquake and tsunami in Japan demonstrated how cascading failures can spread through networks of dependent infrastructure systems. The 2010 Haiti earthquake showed how damaged communication systems can hamper rescue efforts even when international assistance arrives quickly. Recent earthquakes in Turkey highlighted the importance of building code enforcement and revealed how corruption in construction practices can multiply casualty numbers. These international experiences helped California planners identify potential failure modes and develop more robust response strategies. Despite all the preparation efforts underway throughout California, advanced preparedness may be overwhelmed given computer models showing very high casualty and infrastructure impact potential. The next major San Andreas earthquake could affect more people than any natural disaster in United States history. The economic losses could exceed anything the nation has experienced from earthquakes, hurricanes, or other natural hazards. Supply chain disruptions could affect the entire country because California's economy represents such a large portion of national economic output. The retrofitting programs, early warning systems, emergency response improvements, and community preparedness initiatives represent the most comprehensive earthquake preparation effort in human history. California has invested billions of dollars and decades of effort in reducing earthquake risk and improving disaster response capabilities. However, the scale of destruction that computer models predict for the next major earthquake exceeds the capacity of any preparation program to prevent entirely. The goal of all these efforts is not to eliminate earthquake risk, which is impossible, but to reduce casualties and speed recovery from an event that will challenge every aspect of California's society and economy. All of these preparation efforts are based on scientific understanding that existed before 2025, but recent geological investigations have uncovered evidence that changes fundamental assumptions about what California's earthquake future actually revelation. Deep drilling operations conducted throughout 2025 have uncovered geological evidence that fundamentally changes everything scientists thought they understood about the San Andreas fault system. Teams of researchers using advanced drilling equipment penetrated deeper into the fault zone than any previous investigation, extracting rock cores from depths exceeding 15 kilometers below the surface. Hudson's paper documents how deep cores from the Salton Sea region reveal interconnected fault fractures at 15-kilometer depth, providing direct evidence of previously unknown connections between fault segments. These core samples contain mineral formations and stress indicators that tell a story about fault behavior that contradicts decades of established geological theory. The core sampling revealed previously unknown connections between fault segments that scientists had always treated as separate, independent systems. Microscopic analysis of the rock samples shows matching mineral signatures and stress patterns that indicate the northern, central, and southern sections of the San Andreas fault have ruptured together during prehistoric events. These connections exist deep underground where traditional surface mapping techniques couldn't detect them. The fault segments that appear separate on the surface are actually linked by complex networks of fractures and subsidiary faults that extend far deeper into the Earth's crust than anyone realized. Advanced drilling techniques allowed researchers to extract intact rock cores from the deepest parts of the fault zone, preserving delicate geological structures that reveal how the fault system operates under extreme stress conditions. The cores contain layers of crushed and reformed rock that formed during massive prehistoric earthquakes. Chemical analysis of these layers shows that they formed under stress conditions far exceeding anything measured during historical California earthquakes. Mineral thermometry indicates temperatures up to 1,800 degrees Fahrenheit during past slips, and the extreme heat signature suggests high-magnitude events reaching 6.9 to 7.0 in central sections according to CC data. The implications of discovering these previously unknown fault connections transforms scientific understanding of California's seismic hazard. If multiple segments of the San Andreas fault can rupture simultaneously, the resulting earthquake would release energy equivalent to several individual segment ruptures occurring at the same time. Computer models based on the new geological evidence suggest that a multi-segment rupture could produce ground-shaking intensities that exceed current building code requirements throughout much of California. The affected area would stretch from the Mexican border to north of San Francisco, encompassing virtually every major population center in the state. The 2025 data reveals stress transfer mechanisms operating between fault segments that previous monitoring systems couldn't detect. High-resolution seismic imaging shows that when stress accumulates in one section of the fault system, it creates corresponding stress changes in other sections through deep underground connections. These stress transfer processes operate much faster than scientists previously understood, meaning that critical stress levels could develop simultaneously across multiple fault segments rather than building up gradually over centuries in each individual section. Evidence pointing to magnitude 8 earthquake potential comes from multiple independent sources that all reached the same disturbing conclusion. Paleoseismic trenching studies found geological signatures of prehistoric surface ruptures extending up to 350 kilometers, indicating earthquakes that involved movement along connected fault segments. Ground-penetrating radar surveys detected subsurface fault traces that connect previously separate segments through complex networks of fractures. Stress modeling based on current plate motion rates shows that enough energy has accumulated across the entire fault system to power a magnitude 8 earthquake if all segments were to rupture together. The deep drilling operations also uncovered evidence of cyclical behavior in the fault system that operates on timescales longer than historical earthquake records. Rock cores from multiple drilling sites show matching sequences of mineral deposits that formed during periods of intense seismic activity, separated by longer quiet intervals. These geological markers indicate that the San Andreas fault system experiences periods when multiple major earthquakes occur within relatively short time spans, followed by centuries of reduced activity. The current stress conditions across the fault system match the geological signatures that preceded previous periods of intense seismic activity. Seismic imaging technology deployed during the 2025 research campaign mapped the three-dimensional structure of the fault zone with unprecedented detail. The imaging reveals that the fault system extends much deeper into the Earth's crust than previous studies indicated, with some sections reaching depths of over 25 kilometers. At these depths, the fault zone becomes much wider and more complex, with multiple parallel fractures and connecting faults that could all participate in a major rupture event. The deep structure shows that the San Andreas fault system has far greater energy storage capacity than scientists calculated using surface measurements alone. The discovery changes everything about California's seismic future by revealing that the state faces potential earthquake scenarios that exceed all previous planning assumptions. Emergency response plans, building codes, and risk assessments are all based on the assumption that major earthquakes will affect regional areas rather than the entire state simultaneously. A multi-segment rupture would overwhelm emergency response capabilities because damage would occur across such a vast area that mutual aid agreements between different regions wouldn't be effective. The economic impact of a statewide earthquake event would exceed anything the United States has ever experienced from natural disasters. All the previous evidence discussed throughout this investigation now connects to this ultimate revelation about the fault system's true capabilities. The stress accumulation measured in all three fault segments makes sense when viewed as preparation for a system-wide rupture event. The prehistoric mega-earthquakes revealed by paleoseismic research represent examples of multi-segment ruptures that the fault system has produced before. The missing moderating influence of ancient Lake Kauai removes a natural safety valve that once helped prevent system-wide ruptures. The population growth and infrastructure development across California creates vulnerability to statewide earthquake impacts that didn't exist during previous multi-segment events. The San Andreas fault system may be capable of producing the largest earthquake in North American recorded history through a scenario that involves simultaneous rupture of multiple fault segments. Current monitoring data suggests that these critical conditions may be approaching faster than previous estimates indicated, potentially within decades rather than centuries. This magnitude 8 earthquake potential represents a seismic threat that could affect virtually every resident of the most populous state in America, challenging every assumption about disaster preparedness and recovery in ways that no previous generation has ever faced. The scientific discoveries from 2025 reveal a fault system with capabilities that dwarf anything in California's recorded history. Over 39 million people now live across areas that were largely uninhabited during previous major seismic events, creating vulnerability on an unprecedented scale. The potential for magnitude 8 earthquakes affecting multiple regions simultaneously represents a seismic threat beyond current planning assumptions. We cannot prevent these earthquakes from occurring, but specific preparation steps can significantly reduce casualties and damage. Every Californian should secure heavy furniture, retrofit soft-story buildings through EBB grants, and participate in the Great California Shakeout Drill. Download the MyShake app for earthquake early warning, follow CA's 7 steps to earthquake safety, and support continued scientific research that helps us understand this geological reality.